things in the universe when you can't just pace it out or take a tape measure, it's very hard. And it's the product of decades of invested, clever thinking about how to know how far away something is that you can't drive to. And it's called the distance ladder.
He's a wizard.
You can Google it. The distance ladder. You start out with nearby objects. We know how to get the distances to those. We use something called parallax, where a nearby star, when Earth is on one side of the sun, you'll see it in front of stars over there. And when we go to the other side of the sun, it's in stars, background stars on the other side.
Now, did you hear that? That is completely false. There's nothing like that goes on. He makes it seem like when you're over here, there's star, and those stars are behind it. Then when you're over there, the other stars behind it. No. Wait till you see what these fucking wizards have convinced the world is true.
And you look at how much that has shifted, that you do the math, it'll tell you how far away the star is. Once you know the baseline of how far away Earth is from one side of the sun to the other. Okay. If the star is farther away, it doesn't shift by as much. And there's a point where it shifts so little you can't measure it. So you need other methods and tools to figure this out, or better telescopes. And those form the bottom rungs of what is a noble ladder.
It's noble. It's noble because it's the science people.
Of inferences made based on those foundational distances called parallax. So that's how we know.
And if you guys know how parallax works, congratulations. It's a utter joke, really. Well, I mean, parallax on Earth is fine. I don't care if you want to do that. And that does work, right? So I'll give you an example. And we're going to see that this is how parallax would work, right? If you have let's say you've got a river, okay? And you said, oh, we don't know how far this river is across. What could we possibly do to figure out, how far this river is? And let's say that right here, there's a bridge. And, well, that doesn't make sense. I mean, you could just walk across the bridge and measure it. Let's get rid of that. So let's just say there's this river, and we don't know how far it is across, but we can start a spot here, and we can start a spot here, and if we can measure that, right, that's your base of your triangle, and then if you can measure the angle, let's say there's a tree here, or whatever, and you can measure the angle here, and you can measure this angle here, and you can figure out the distance between there and there. And if you knew this distance, which we can calculate, right, then you can know the rest of the distance. That's basically parallax in a nutshell. Because what you do is you figure out, this. Well, now what they're saying is, and the drawing that we've all seen before, is one where you go, you've got the Earth, or let's put the sun first. Here's the sun. Okay. You got the sun, and you've got the Earth's orbit, supposedly. Okay. And they say, oh, well, if we take a measurement from here and here, since we know that this is 1 AU, 1 astronomical unit, right? Because it's half the distance here. So this would be 93 million. And this would be 93 million. So you can double that to get to 2 AU, or 186 million miles. Okay. So once they have that baseline of the triangle, okay. So this is, oops, put that back up there. Okay, thank you. So once you have the base of that triangle, just erase that on them. Thank you. Once you have the base of this triangle, which we do, we have this now. There's our base. We know the distance. So they make it look like, oh, well, now if there's a star here, and here's your background stars, then you just measure here, and you measure 6 months later, and then you've got this triangle. And if you know this distance, then you can figure out this angle, and from there you can get the distance of the sides. Okay? That's how they tell us they figure out the stars. Here's the truth of it, though. The truth is that the angle is so tiny that, again, this angle here, that's not correct. Let's get it straight up. Okay, that angle there, this angle here, is 89.999 degrees. And this angle here, the other one over here, is 89.999 degrees. They think they can measure this with the atmosphere, the shit in the sky. Yeah, they'll just measure it. That's how, and you're like, that's not a triangle. No, well, eventually it gets to be a triangle. And then they come up with their nonsense parsecs and their let's show you an example of what I'm talking about just a little better. Let's see. Let's go over to, where are we at here? Describe it again the same way we always hear it, kind of like what I just told you. You know, why, you know, quiet down. So they say, oh, the nearby trees go by slow. This is how they always convince people, right? They give you like reality. Like, okay, yeah, we know that we can measure things with parallax locally. Great. When it comes to the stars in the sky, I mean, look how easy this is. Well, we know it's going around in orbit. And look how they do this. It does not displace like that, folks. If it displaced like that, then your angle would not be 89.99999 degrees, okay? And so they talk about nearby star, but they very, very primitive drawing, like everything's close. This is not at all what they're actually trying to sell you in reality. They basically say, oh, we can draw this triangle over here, and it's that easy. From there, we figure out the distances of stars. Now, if you actually told somebody, get on a telescope and you measure that angle, they'd be lost. Like, I can't really, yeah, we can't. Look how they draw it as if that's what we see. Okay. What would be the angle from here to the star? Like 60, you know, not 89. The real angle is a straight line, straight off there. But they make it seem like it's so easy. We'll just go out there 6 months later. You know what I was thinking too, which is weird, is that you're actually on the other side of the Earth. You know, this would be nighttime over here. And you're over here, nighttime's over there. I was like starting to think, like, is the little tiny angle that they say they measure simply because I wonder if they take it as they're on the other side of the Earth? Because if they do that, now the 186 is what gets them, the 186 million. Or anyway, sorry, I was thinking to myself, trying to figure out if it's just a flat Earth measurement. No, don't think that's right. So anyway, then it tells you how to get the math. And the math is always weird, right? They always have to have their symbol. Why can't it just be something normal? But no, it's got to be the 1AU and the tangent of the sine and the cosine. Of course, always. So that kind of explains it to you a little bit. Now there shows it a little bit more. Okay. And then they say, and this is crazy, I talked about this last week, I think, or something, right? That parallax angles of less than 0.01 arcsecond are very difficult to measure because the Earth's, well, yeah, that's a lot hard. This limits Earth-based telescopes to measuring the distances to stars about 1 over 0.01 or 100 parsecs away. Space-based telescopes can get an accuracy. We have a lot of space-based telescopes out there, which has increased the number of stars whose distances can be measured. No stars' distances can be measured. Stop letting these people run your life, okay? It's nonsense, bullshit. So let's go to this stellar triangle thing here. And this is where you'll start to see that really what they want you to put here is like, all right, I've got 50 meters here and 60 degrees here. And I've got 55 degrees here. And you hit calculate. And then they draw this nice, and you're like, oh, okay. There's my baseline of 50. And then since I know this angle and this angle, I know this angle adds to 180. And then I can figure out the distance of these two sides. This one's 48.192, 47.778. Okay, great. So now here comes the problem. If you put in here 186 million, okay, and we calculate again at those angles, well, 186 million, of course, the sides are 177 million and 188 million. Well, that's not going to work for stars. We need them to be quite a bit further. So you can keep increasing these numbers. Like, well, what if my angle was 80 and this angle was 80? And we're talking about this line, right? So this angle here, B angle. So 80 would be about here, maybe. Let's calculate that. So with 80 degree angles in this, you still get 535 million. Well, that's not enough. 886 million. We need the stars to be a lot further than that. So you do it again. Go back to the drawing board and we go, let's see, what if it's 88 degrees and 88 degrees, which will put this one at 4. Okay. Now we get this kind of triangle, 186 million, but we're still only at 2.6 billion miles. That's not enough. We need them far, far farther than that. So you keep going, and that's like I said, 89.99, and 89.99. We calculate again, and we still are at 186 million going all the way, and still only that is, oh, wait, sorry, that's 532 trillion. Is that correct? And let me see, is this the calculator that tells me? Okay, so this one does a better job of explaining when we get to those big numbers. So do you know what a milliarcsecond is? When I found this out, I'm like, oh my God, these guys are jokers. So think about a circle. Should I bring up my drawing pad? Maybe. just so I can show you what nonsense we're talking about. Let's bring up this and put it over here. All right, so you can see that. Yep. All right. Sorry about the pirate chain logo. We're going to get rid of that. So we know a circle, obviously. Okay. And to think of what 1 degree is, right? So let's say, and my drawing's going to be off. Don't worry. It's just the way. And you can't, that's way too big of a line. Where's this over here? Sorry, I have to fix this and bring this way down to like 5. All right. Bring it back over. All right. So we've got this line here. And then we've got, okay. So really a degree is going to be basically like maybe there-ish. I mean, that's even too much. Okay, so that's your degree, which we know because 90 degrees is here. And so, oops. Stop doing that. 90 degrees would be here. So we know 45 is about here. Okay. And then you can keep going, maybe a little more. 45 is there. Good. And then you can keep cutting that half, and you're going to realize that mine is, probably 2 or 3 degrees, really. But we just want it to be 1. But we'll use that for, there we go. Okay, so this is 1 degree. We're talking about a circle, okay? And now I want you to learn what a well, let's look what an arcsecond is. Okay, so what is this? What is an arcsecond? It's a 60th of a minute of time, which is the SI unit is defined. Whoops, that's not the one I want. What is 1 arcsecond? It represents the distance of latitude and longitude traversed by the Earth's surface when traveling 1 second. 1/3600th of a degree. Okay, so now go back to our drawing and imagine that we take this little sliver here, and we need to come up with 1/36,000th or 3,600th of a degree. Okay, so now we've got to split this little line into 3,600 marks. 3,600 marks, and that gives us 1 arc second. Okay. Now, if that's what they were measuring, maybe I could believe it. Maybe. That's not what they're measuring. Let's find out what the hell a milliarcsecond is. Milliarcsecond. Okay, milliarcsecond is the unit of angle equal to 1/1000th of an arc second. 1/1000th? This is delusional, folks. Once we've split this little tiny angle into 3,600 check marks, then take one of those little 3,600 check marks and 1/1000th of that is a milliarcsecond. Now let's go back to our little calculator here, and you'll notice that this is measured in milliarcseconds. Now you can change it to arc seconds, but if I try to put 1 arcsecond, well, here's the problem with that. It will be 1 parsec. That's how their math works. In fact, that's why it was done that way. So 1 arcsecond is 1 parsec, and then from there, we could put 0. If you try and do 2, it's impossible. There's no such thing as 2 arcseconds, because if we calculate that, nope, sorry, can't do that. Not allowed. You can only do arcseconds. What? Okay. Can we? What if it's 1 degree? No, we don't do that. We only do arcsecond, milliarcseconds. Okay, what about 0.01 arcseconds? Think of what I just said. 0.01 arcseconds is 100 parsecs. Then you can go to milliarcseconds, and you can get, I don't know if it'll let us do 0.1 of that. Let's see. That's 100,000 parsecs, or 300. That's only 326,000 light years. But we hear them talk about millions and billions of light years. Okay? That's insanity that anybody believes this. And you can even go further. You can take that to 0.001. And you're still not out of the, now you're at 3 million light years. Okay? But think about what I just said. That's 0.001 milliarcseconds. We just said that the drawing 1/3600th, split that one little piece, split it into 1,000, and then 0.001 of that, that's another 1,000. That's delusional thinking. Okay? To think that we've given these guys, and why nobody questions it, and they say, no, we know how far the stars are. How? Show us. Show us you can figure this out. Imagine the change that it would be that tiny, which is why no astronomer in the past ever tried to claim that they could do that. And now they just claim they can, but have you ever seen it? You ever seen anybody measure this? Me neither. And to think that, you're on one side of the Earth's orbit to the other side, and then we measure, and that's all the change that there is. Aren't all the stars moving? I thought so no matter how far those distant stars are, you're saying that us moving in a half a year, and those stars must have not moved at all. Because if they moved a smidgen, then that's where you're getting your distance from. And you're completely off. Completely off. So it's a joke that anybody believes this. And I get it. When you're talking about being close and you're like, well, I can measure this and it's 20 feet. And I can tell. Let me actually calculate that with 89.99. What does that come out to? So if we had that, the equivalent of that. So if we had a baseline of 20 feet. Okay, that's about a driveway width. Okay, so if I got my driveway width as the baseline, and I were able to measure 89.99 degrees on one side and 89.99 degrees on the other side, I'm looking 57,000 feet, which is 10, 11, 12 miles. So I'm able to see, so the length of that would be 12 miles. I mean, that's just insanity. It's insanity that they're claiming they can see that. And you can see what their triangle looks like. It's a pretty triangle, isn't it? Pretty triangle. I mean, it's just a joke. I mean, parallax I could see working when you're talking about a normal triangle. But it has to be normal. I could see it working if my driveway's 20 and you're like, well, this is 70 and this is 40. And then you calculate, you're like, okay, this is what your triangle looks like. Here's your driveway. The distance to that item is 13 feet and 20 feet. Okay, great. But beyond that, sure, could you go, this is 85 and this is 80? Sure, calculate that. Looks like that. And we're able to figure out with my 20-foot driveway, 76 feet and 76 feet. Okay. Not when you're getting into insane numbers that you need to have happen. And then when he talks about it's a noble ladder, this is just, and then you say, well, how do you get the stars that are further than that? And the other thing is, I thought that you can do parallax measuring. If you do parallax measurement to Mars, okay. How is parallax calculated on Mars? How do we measure the distance to Mars? Using triangulation, Cassini was able to make a measurement to the distance of Mars. He calculated a distance of about 140 million kilometers, which is only off by 7%. What changes when doing parallax measurements from Mars compared to Earth? Measuring stellar parallax on Mars would allow the measurement of the distances of the stars 1.5 times further away. What? Don't know what they're talking about. I thought that, how do we use stellar parallax to determine the star's distance? And where there is somewhere that I've seen where it says that they use parallax to figure out the distance of Mars and Venus, but that the other planets are too far. Wait, what? Well, I got to see if I can find that because that makes no sense. So we can do it to close planets, but not the far ones, but the far stars we can. Can we use parallax? Oops. Parallax for Venus distance. The parallax principle and Kepler's laws, discovered by analyzing objects, yeah, sure, are sufficient to allow us to measure the distance from Earth to Venus, and hence all the distances of the planets from the Sun. That's not even correct. I don't know why they say shit like that. How far can we use the parallax method? Limitations of distance measurement using stellar parallax. The limits Earth-based telescopes to measuring the distant stars to about 1 out of 100 parsecs away. Okay, see again, why would they say this if they just told us we can use it for Mars? Stupid. Parallax transit, Venus transit parallax measurements. Measuring the size of the solar system, parallax. Now, I think if I put in, can we use parallax for Saturn distance? Now it's going to say no, which makes no sense. Let's see here. Stellar parallax. Astronomers can use effects called parallax to measure distance to nearby stars. I'm trying to look for planets. We want to use the largest distance we can, the bright star Vega. No. How to calculate the distance to planets using parallax. Let me see here. How to calculate. Here, two distant observers on widely separated points on Earth can take simultaneous photos of a planet through a high-powered telescope. Compare them. And again, they always say that. None of these guys have ever done it. Through a high-powered telescope. What do you mean high-powered telescope? You mean a telescope with a bigger mirror? Woo! Wow. Look at you guys. Compare the photos and estimate the parallactic shift. Then use straight line distance between observers and your baseline. Simple geometry. Simple geometry, you know. Bear in mind that any parallactic shift will be very small. Yeah, what about, are you talking about planets or the stars? Okay, it depends on what coordinate you have and what parallax. That doesn't make any sense. What is it? Let me find it. I hate when I say something and then. Can we measure parallax with a greater accuracy? Earth's orbit. Mars. Okay, here we go. Oh, no, that's Mars or, nope, Mars or Saturn have a different one. Saturn's parallax measurements. Parallax is one of the most important distance measurement tools. It's the most important used by astronomers and can only be used for nearby stars. Okay. But it is very accurate. Yeah, they know that. And we would know things are very accurate, just like when we do a triangle in my driveway, because we can go out and fucking measure it and show that it's very accurate. You cannot say it's very accurate when you just say it. Yeah, it's about 75 trillion miles over to that star. Yeah, very accurate. Very accurate. We measured it one time with, the same method that we're using today, but it's very accurate. Oh, okay, makes sense. The same effect can be used. I mean, here we go. These pictures are for fucking children. And they just convince me, like, oh, that's how they do it. They know the distance of a star because they do this. Even though, like I said, we're talking 90-degree angles coming off here. And you can tell that they're bullshitting when they talk about the distance to the object, which has a parallax angle of p of 1 arcsecond. But that's not true for anything that except for the stars. They like make their own rules to these different fucking games. Would it be easier to measure a star's parallax from Jupiter? It's so stupid people ask that question. Yeah, I just told you that we're talking a baseline, and however big the baseline is, would be more accurate. How do we measure distance in space? How do you measure distance when you're flying in space? That's the thing I've never understood. You got, let's send this craft out there. It's going to fly to Pluto. How do we know how fast it's going? How do we know what distance it's going? I don't know, because we measure with the pitot tubes. Nope, there's no air out there. There's no atmosphere. Oh, we measure by ground distance. Nope, there's no ground out there. It's just empty space. You're just flying through nothing. Oh, yeah. The speedometer. No, how does the speedometer work? Where is it getting its reading from? I don't know that then. I think that their answer is, like everything. Oh, we can bounce signals off of it. Cool. But anyway, I don't see. Let's see here. Parallax for Saturn distance. If we use the parallax, let's see what this one says. In September, Saturn is 9.9 AU away from Earth. If we use parallax method, what should be the baseline between the two people? So I know D equals whatever, but how do I find out theta? I'm pretty sure the answer is pretty obvious, but my mind is really not working right now. Any appreciation? Are you treating as the only unknown? You believe you know the baseline distance exactly? If so, then you compare your angular sighting of the distant star, like we talked about, versus Saturn with the same for the other observer. The devil is in the error analysis. Your two angles will be absurdly close to each other in magnitude. So imagine, that's what he's saying about a planet that's close. Be careful, your angles will be so tiny. Well, what about when we measure the distant stars? Because they're a little bit further than Saturn, according to you guys. Your two angles will be absurdly close to each other in magnitude, which means a very small error in value leads to a large error in calculated distance. Yeah, I think so. So a very small error on our Earth-based, but no, astronomers do that with a very high-powered telescope. High-powered telescope. What the fuck does that mean? You should find some first-year level text on measurement and statistical error analysis to get a better feel of the difficulty here. Of course, it's difficult, but we believe it. These guys, they would never lie to us. Measuring parallax of the planet. Saturn lies approximately 2 billion kilometers from Earth. 2 observers, 13. Let's see here. And of course, they always like to give you the answers too, right? Yeah, of course. Looking at the planet would measure what parallax. What? Thought it was going to give me an answer. I don't know why everything's so easy to find the first time. They basically say you cannot use parallax for the close things. You can use it for very close, not the planets in the back, and then for the stars again. Makes sense. Could we measure parallax with great? Yeah, I already read that one. Parallax measured to star, whatever. Parallax. Astronomers use the effect called parallax measure distances, apparent displacement of a star. Yeah, no. I'll just one more thing. Can you use parallax for planets? Planets. here you go. Now, we just saw something different 2 seconds ago. The parallax principle is not sufficient to determine all the distances in the solar system. Only the planets Mars and Venus and asteroids like Eros that pass close to the Earth are accessible. Does this make any sense to anybody? So we can only use the close planets and the far stars. What? Fucking stop making shit up. The sun and the other planets are too distant, but Kepler's laws allow the problem. Yeah, wait, I didn't think about that. Oh, you would never be able to do it because you can't see what's behind the sun. Huh. Wonder on an eclipse day, I've never really seen stars behind there. If you had two people with a baseline looking at the sun on an eclipse day to see what it does in the background, let's just pretend. I just want to see what we come up with. So let's our triangle. Let's say that we've got two people, different sides of the United States. So we're talking 2,500 miles. And both people will be looking at the sun. So let's say it's noon for New York. Yeah, I mean, again, you're going to have such tiny angles. That's the problem. You're going to have 89 for that person. You're going to have 89 for this person. What distance does that put it at? Where's my... Oops, where'd it go here? Where's my answer? What did I say this distance was? We said 2,500 miles. Where's that at? Oh, here we go. Wait, what? Heights. What? Am I getting confused here? No, we're both looking at the sun. So this distance is 2,500 miles. What did I put in here? 2,500. Yeah. Why isn't one of the answers, where's the base? It should be 2,500. Wait, what? Well, let me change these numbers real quick. I need to see something. I'm getting confusing myself now. Which one is each side? Okay, so this is C. So C should be, what? Height C? Okay, I'll just look up here. Side C. Why does height C say 4,627? Height C? C is this. Am I doing something wrong? I'm just lost. Maybe it's getting too late. So side C is 2,500. Okay, so that's 2,500 miles, yes. And then if we had these angles, then, the sun would be 4,000 miles away. But if we get those at, let's go 88 and 88. See if we get here. Okay, so that's, 2,500, and then it would be 35,000 miles. But again, the problem is that the same thing we know already. Like Dave shows with the paper towel and the light in the back, that we're not looking at the actual sun. So you're not. But the reason that they don't allow this is because you're going to get the wrong measurement, right? And we've done this. We've done this, and it comes out to 3,900, right? When they've done this, if you do try and calculate the distance to the sun, you get a baseline of whatever. Like if you do the sun from let's say it's above the equator, so it's on the equinox. So that the person in Ecuador measures 90, and we would know that a person at 45 degrees would measure 45 degrees, right? And if you calculate that, you're going to get the height of the sun, which is, there you go, which is 35,000 miles. So again, somebody at the equator is looking up, sun. Somebody at 45 degrees north, looking 45 degrees to the sun, 2,500 miles between them. Oh, well, no, that would be more than that. What is the distance between, what is it? 70 miles per degree. So I just go 70 times 45. I think it's about right. 70 times 45 equals 3,150. All right, that's better. So then 3,150, I'll put it at 3,959. 3,150. Calculate. Now it's going to be 4,454. A little higher than I thought. So 3,150 is also this. Oh, because we did 90. All right. Yeah, there's so many problems with this. And let's check out that one video that I have left, and then we will get to talk to you guys. Is it long? I don't remember how long it is. Let's see here. NASA genius technique that measures stars. Wait, is this that guy? Oh, the Astrum. I didn't know it was this guy does it. Oh boy, I got to hear this guy real quick.
You may
So
have
beautiful.
wondered, with
How'd
the
they do
vast
it?
distances between objects
Yeah.
in space, and with the lack of a tape measure that big,
Yeah.
how can scientists be sure they know the distances
how they be
between us
sure?
and other celestial
Please
bodies?
tell us.
Well, there are a few methods
Ooh,
available
a
depending
few.
on how far away the object is,
Mm-hmm.
each with a varying degree of accuracy.
Mm-hmm.
The first method is the most accurate, and in fact gives us very precise measurements.
Very precise.
This is the parallax method.
So precise.
For those of you that don't know what the parallax effect is, it is where nearby objects appear to move
See how like
more.
everybody just repeats things? What if this is my job every day? Parallax is great, guys. Let me explain it to you. When you have this Earth and we go around the sun, we all know that. No, not flat earthers, the crazy idiots. And then they measure the angle to the background stars off the close star. And the angles vary. Then you just do some simple geometry. And you have a high-powered telescope and boom, you know the
objects far away
distances.
as you travel parallel to them.
Oh.
For instance, when you look,
Let's do a super simple diagram that doesn't make any sense.
until about a distance of 400.
Yeah, do you know what this fucking angle is? This angle is about 45 degrees. Do you know what the real angle is? It's a fucking straight line off here about 89.999 degrees. We measure it though, it's very easy.
As beyond that, the change in its apparent motion can't be measured anymore.
Can't?
Earth's orbit would have to be a lot bigger before you could use this method for farther distances. Which is unfortunate because most things in space are further than 400 light years away from us. But thankfully, there are very clever scientists out there
Thank
that
God.
have come up with another
Thank you,
method
God.
to judge distances.
Don't tell me
without
Cepheid
having
stars.
to use trigonometry.
Don't say Cepheid stars.
Although it should be mentioned that this method is slightly less accurate.
Don't say Cepheid stars.
It's just simply the best we've got.
Okay.
It seems that stars tend to follow a pattern,
Oh, here we go.
which can be seen on this chart.
Oh.
Main
yeah.
sequence stars, which make up the majority.
Yeah, we just looked through the atmosphere and then we said, which one does it match? Well, it's a little bit red, then it's down here, and then we draw it over the line over here and we know the distance. That makes a lot of sense.
Of stars in the universe
Mm-hmm.
can all be found somewhere along this band.
Sure.
Their temperature corresponds to their color,
Yes.
and most importantly, their brightness.
Yes, the brightness and color.
Using stars that have a confirmed distance thanks to the parallax method,
Oh, the confirmed distance from the very accurate parallax method. From that, we can then calculate it. I
we
get
can
it.
see how much a star dims due to the distance between it and us.
We can see how much a star dims. What the fuck is this world coming to when we've believed these guys?
And extrapolate that far beyond 400
Close, we
light years.
extrapolate all
Say
the way.
we see a very blue star.
I see a very blue
that we
one.
want to know the distance to.
Yes.
Once we know the star's precise color,
Oh, right here. Oh,
we
we're
can
there?
tell how
Okay,
bright
there.
it would be if it were right next to us.
Okay.
We can then measure the star to see how bright it is from
What?
our perspective.
Well, that makes a lot of sense.
Combining this with our extrapolated data,
Right.
we can predict how far away the star really
See how they talk to people and people are like, oh, I get it. They do
is.
know.
Obviously, though, there is some margin of error in our
Yeah, you
predictions.
think?
This band is quite thick after all.
What about
not a
this
precise
band?
thin line. So these two methods work for stars in our own galaxy, where they
Oh.
are still close enough to be resolved individually.
No.
But what about other galaxies?
Yeah, what about them? How
do
you
we
do
measure
that?
the distances
Seems
to
very
them?
impossible to me.
Well, we would have struggled were it not for the universe being
No,
kind
not
to us
Cephids.
by gifting us.
Listen to this.
Cepheid
I read this earlier.
variables.
Listen to this.
A Cepheid variable is a very special type of star.
Very
that
special.
changes in brightness periodically,
Oh.
depending on how bright it is.
What?
And some of these stars are very bright indeed. So much so that the changes in brightness can be detected by us all the way in a different galaxy.
Sure they can.
Timing the pulses in a Cepheid variable, we can know exactly how bright the Cepheid variable should be and how dim it is to us, allowing us to use the extrapolated data
Then
again
extrapolate
to
again?
work out the distance to it
Easy.
and to the galaxy. it
Simple
resides in.
geometry.
Beyond that,
How did
it
not people not
gets
believe these
much
guys?
more complicated and less accurate.
Oh,
With galaxies billions of light years away,
yes.
you have to start taking into account the expansion of the universe and
Oh.
redshift.
Mm.
And the distances make seeing the galaxies at all very difficult.
But we know the distances. I mean, science is beautiful. I'm going to hold off on the Pluto video, but I'm going to write myself a note that we still play that next week for space time.